An astronaut on the moon is protected from the harsh environment by a carefully designed spacesuit. He needn't worry about the vacuum of space or the extreme temperatures on the moon. But there is another invisible menace which could cause him harm. Exposure to radiation from charged particles flowing out into space from the sun. This continuous stream of matter is called solar wind. And the spacesuit does not adequately protect him from the dramatic surges in the number of particles. More than 3,000 years ago, Chinese astronomers observed dark spots on the surface of the sun. Today we know these spots are actually zones of intense magnetic activity. Sunspots like this one spawn other solar activity such as flares and prominences. Fiery plumes of glowing gas that sometimes surge to heights of more than 150,000 kilometers above the surface of the sun, or 12 times the diameter of the Earth. Each massive solar eruption propels an added burst of charged particles out into space. Since individual particles take up to 2 days to reach the Earth, an increase in the number of sunspots and solar flares acts as a signal to scientists that the solar wind will intensify, becoming a torrent of deadly radiation streaming towards us. Fortunately for all life on Earth, the magnetic field surrounding our planet protects us from this danger. But how? Remember that a conductor carrying a flow of charge within a magnetic field experiences a force that is perpendicular to both the field and the flow of charge. This force will also be present whether the charge is flowing through a metal conductor or even freely in space. Each moving charged particle has its own magnetic field. The circular field of a negative particle is in this direction, causing the two fields to react here. The motor principle dictates that this repulsion pushes the negative particle to the left. However, the solar wind consists of both negatively and positively charged particles, and their fields are in opposite directions. Positive particles, then, deflect off the other way. So when the solar wind encounters the Earth's magnetic field, the charged particles tend to separate, with the negatively charged particles being deflected around one side of the Earth and the positively charged particles around the other side. The result is that most of the particles are deflected and never reach the surface. However, not all of the particles get away so easily. Some become trapped for a while in two large donut-shaped areas called the Van Allen belts, centered above the equator. The inner belt extends 1,000 to 5,000 kilometers above the surface, while the outer belt extends 15 to 25,000 kilometers. Occasionally, particles from these belts filter down to the atmosphere and are guided by the Earth's magnetic field toward the North and South poles. Near the poles, they collide with and excite atoms and molecules in the atmosphere, which release the excess energy as light. In the North, the resulting ghostly light display is called aurora borealis, or northern lights. In the south, it's called aurora australis. Every time there's a display of northern lights, there is a simultaneous display of southern lights. At times, these displays are quite spectacular, visual evidence that a gust in the solar wind has occurred. These gusts, which are the consequence of sunspots and other solar activities, occur in cycles. One theory holds that during periods of unusually low solar activity, glaciers advance and the survival of plants and animals is threatened. But then, with the return of high solar activity, glaciers retreat and life flourishes in a more favorable climate. So far, we've been dealing with the results of solar magnetic fluctuations. Throughout its long history, Earth has experienced periodic fluctuations in its own magnetic field. Geophysicists believe that the Earth's magnetic field is actually produced by complex movements of charges within the molten core of the planet. This flow of charge seems to reverse, on the average about every 200,000 years, resulting in a reversal of the north and south poles. The flow of charge within the core mysteriously slows down, reducing the magnetic field to about 10% of its normal strength. With a dramatically weakened magnetic field, the solar wind is no longer deflected around the Earth, and so the charged particles rain down on the surface. This can disrupt the genetic materials within the living cells. Subsequent mutation may account for the sudden extinction of many plants and animals, and the appearance of whole new species. Then, the weakened magnetic field reverses and returns to full strength. A few species have actually evolved with the remarkable ability to take advantage of the Earth's magnetic field. It is well known that homing pigeons use the sun for navigation. Less known is the ease with which they navigate on days when the sun is obscured. However, in experiments where pigeons were equipped with earmuffs containing tiny magnets, it was found that they soon became disoriented on cloudy days when they couldn't depend on the sun for navigation. When the earmuffs were removed, these same birds recovered quickly and easily reached their destination. Magnetic material in the pigeon's brain somehow allows the pigeon to fly as if it has a compass inside its head. Even microorganisms have this fascinating ability. Certain types of mud bacteria have learned to use the inclined magnetic field of the Earth to determine up from down. In Australia, the field direction is upward, and so bacteria go against the field when moving deeper into the Earth in search of moisture. When these bacteria are brought to the northern hemisphere, they're fooled by the switch in the magnetic field direction and navigate upward instead of downward. This brings them to the surface, where they dry out and die. It's the presence of the magnetic field that originally helped make Earth a cozy planet for living creatures. And it was an understanding of magnetism that enabled those courageous few to spread out and explore the unknown face of Earth.